Okay, so I'm going to give you a video on the Bohr model. Now, this is not in Atkins, and we actually won't use some of this mathematics until we get to the later part of Focus 7. But I think it's important for you to be familiar with just the mental exercise of thinking mathematically of systems. And starting with quantum systems is quite challenging. And so we're going to start with the Bohr model because I think it's a little bit easier to see some of the approximations that we make. Keep in mind, this is not the correct model. And so it is not that this is set in stone, but it's really helpful to see the thought process of deriving the Bohr model, or I should say the quantized energy of the Bohr model state. Okay, so here's a Bohr model. So you've got a nucleus, it has a mass, and an electron. We'll put its mass right here. And there's a radius between the two. And so this has a charge of the number of protons, Z, times the electronic charge. And this is a negative electron. Okay. So the idea behind the Bohr model is that the force between the nucleus and the electron is balanced. Okay, so in the previous video, I talked about how you had the attraction here is equal and opposite to the centripetal force this direction. So we have the centripetal force, center-seeking force going this way, is equal to the Coulombic force, which is the fact that you've got a positive and a negative. So Coulombic, the force between them is equal to 1/r squared. And so here we have the centripetal forces in balance with the Coulombic force. So m sub e u squared over r is equal to z e squared over 4 pi epsilon 0 r squared. What do all of these terms mean? Okay, so this is the mass of the nucleus. U is equal to the velocity. So mass times velocity squared over r. R is the distance between the two. Here you have the nuclear charge, or sorry, oh my gosh, the number of protons. So the number of charges multiplied by the charge squared over 4 pi epsilon naught. Epsilon naught is the permittivity of free space. It's basically a way to get the units correct, but also this tells you how well electric fields can permeate through a material or through free space. If it's not that, it's called the permittivity. If it's actually a material, and that would be known as the dielectric constant. Okay, and then r squared, same r, it's the radius between the two. Okay, so let's zoom in here and ask ourselves, what is this mass? So we've got the mass of the nucleus, mass of the electron, there's an r between them. Here you have the center of mass. And so this center of mass becomes the axis of rotation around which the electron and the nucleus rotate, okay? And so this center of mass along with the rotation becomes the reduced mass mu, which is equal to the mass of the nucleus times the mass of the electron divided by the sum of the two. And this approximately equals, because the mass of the electron is so much less than the mass of the nucleus, this becomes big number plus teeny, 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 tiny number, which is practically just m sub n, which means m sub n's cancel, which is approximately equal to the mass of the electron. So that says that we can really think of the nucleus as stable, and the electron is then spinning, I will say orbiting, around the outside. Okay? All right. So in the Bohr model, you've got the reduced mass is essentially equal to the mass of the electron. Okay, everyone cool? All right, so I'm going to write here and then move back up. So in the Bohr model, we're going to say that L, the angular momentum, which is L, is equal to m sub e u times r, where u is equal to the velocity. Okay, and the reason I'm not using v is because we're going to introduce a quantum number pretty soon called v in about 4 chapters from now, and that's anyway. So u is going to be the velocity. So this is equal to nh bar. All right, and so this is the quantized energy state. Okay, so if I then, so here we're saying, okay, so this angular momentum is quantized. It's part of the Bohr model. That angular momentum can only come in these discrete packets of energy. Okay, and so those discrete packets of energy can be some quantity n times h bar, and h bar is Planck's constant divided by 2 pi. So h bar is equal to h over 2 pi, which is equal to 6.626 times 10 to the minus 34 joule seconds divided by 2 pi. You see Planck's constant divided by 2 pi so often that we just lump it in and we call it h bar. You'll get used to it. Okay, so we've got integer number quantities of h bar is equal to our angular momentum, okay, which basically says the angular momentum of this electron around the nucleus can only be set values. Okay, all right, so now I'm going to, so if I solve for velocity, u is equal to nh bar over m sub e r. Cool, so I'm going to take this and I'm going to plug it in right there. Cool, pause. Okay, so I've got, this is the original equation that I wrote, m sub e u squared divided by r is equal to, this is the Coulombic attraction, or the potential between the two positive and negative charge. I've substituted in the velocity from the quantized angular momentum equation. So velocity was equal to nh bar, there's the quantization, divided by reduced mass times r. That's squared because you got u squared. So now what I'm going to do, notice how I have an R, and an R. I'm going to just solve for R. So get R on one side of the equation and everything else on the other. So if I do that, solve for R, R equals n squared, h squared, epsilon 0 divided by pi mu z e squared. Go team! Okay, so I can define then that all of this stuff, actually, I'm going to rewrite this with the z right here. Is that cool? I've just moved the z over. And also, just to note, I write all of my z's with a little bar in the middle, just because z's look like 2's. You might want to do the same. We'll have quite a few z's. Okay, so I'm going to say that all of this stuff, I'm going to define A0 equals h squared epsilon naught over pi mu e squared. This is equal to what's called the Bohr radius. Whoops, Bohr HR radius, which is equal to 5.29 times 10, 52.9 times 10 to the minus 12 meters. And I'll tell you what that is in a second. Okay, so if that's the case, that means R is equal to A0 equals to n squared A0 over Z. All right, so what this says, R, what is R? R is the distance here. So that's saying that the distance of the electron from the nucleus can be in units of n squared, where n equals 1, 2, 3, and so on. So it can either be 1 times A0 over Z, where Z is the number of the positive charge, or the number of positive charges in the nucleus. So it can be 1 A0 over Z, so this could be A0 over Z for n equals 1. For n equals 2, this distance would be 4 A0 over Z. For 3, it would be 9 A0 over Z. So we have these quantized or discrete orbits that the electron can be found in these shells around the central nucleus. Okay, so that is the Bohr model, or part of the Bohr model, is that you have these quantized radial orbits of the position in which the electron can be found. Cool? Okay. So now I'm going to take it a step further, and the Bohr model tells us, one, that there's a discrete location of R that the electron can be found, and the other thing is that its total energy, which is kinetic plus potential, is going to equal, so we've got, so the potential energy is 1/2 mu u squared. This is 1/2 mv squared, but So any kinetic energy is going to be 1/2 mv squared. M is our reduced mass, U is our velocity squared, plus I've got now minus ZE squared over 4 pi epsilon naught R. This is my Coulombic potential. So kinetic energy, Coulombic potential. Okay, and we knew that because we said that the Coulombic potential, or the potential energy, was equal to the centripetal force going out. Well, I guess this Coulombic potential is equal to this centripetal force. All right. And so we know that the total kinetic energy, or the total energy of our system, kinetic plus potential, should be this sum. And so from what I had done earlier, I can say that this, whoops, mu u squared is equal to 1/2 ZE squared over 4 pi epsilon 0 R. Now this comes from what we did in the prior board, minus ZE squared over 4 pi epsilon naught R. Okay, and recall now that we know what R is. So R equals n squared A0 over Z, where A0 is the Bohr radius, which means that the energy is equal to Z squared E squared over 8 pi epsilon naught n squared A0 minus ZE squared over 4 pi epsilon naught n squared A0. And that comes down to, when you combine these two, the energy equals minus Z squared E squared over 8 pi epsilon naught n squared A0. I should have just written that down instead of just talked out as I wrote it. Okay, what does this say? Equals E. Two questions. Any quantum system, as in the atomic system, you have two questions. Where are the electrons and what is their energy? The Bohr model says the electrons are found here at an r distance away, depending on the quantum state, n, and the number of protons that you have. So that will tell you where they are. This tells you what their energy is. And notice their energy can be in integer quantized states. Okay, so you've got, for example, if you said for the n equals 1 state of the hydrogen atom in Z equals 1, this energy equals minus 13.6 electron volts, which corresponds to an energy, the energy necessary to ionize the, so for a hydrogen atom, if you have a proton and the electron, the amount of energy necessary to ionize this first electron, or the only electron in the hydrogen atom, is minus 13.6 electron volts, or 2.1 or negative 2.17 times 10 to the minus 18 joules. 13 is easier to remember in terms of electron volts. Anyway, so what is this saying? This is saying that the Bohr model tells you that there's quantized radial regime, or a radial point in which, or a shell in which the electron can be found. It also tells you that the energies of those electrons are quantized, which means they can be in discrete values. They can't be, there's not a continuous number that they can have. There's quantization of allowed energy states. Okay, so let's tie this all together. So the assumptions of the Bohr model. 1, we have that the electron rotates around a nucleus in a circular orbit. Number 2, the electron remains in that circular orbit, and the electron doesn't plummet in. Number 3, angular momentum in each stationary state is quantized. We know that because it's quantized by the discrete energies associated with this, so the nucleus and the electron. So by this balance of forces of the Coulombic and the centripetal force, by that balance, you have these quantized energy states. The other thing that we know from the Bohr model is that radiation is emitted or absorbed in these electron jumps, to where you've got, so this is the n equals 1, n equals 2, n equals 3. So the electron can jump. If it absorbs a photon of energy, h nu, it's going to absorb a photon and it's going to jump up, or it's going to jump up if it has the energy between n equals 1 and n equals 3. That's all from the Bohr model. and the frequency of the emitted or absorbed radiation is equal to the energy differences. So the energy, let's say that this electron jumps back down, it emits then this radiation, so delta E is equal to h nu of the emitted radiation, which is equal to E3 minus E1 if we go from here to here. So the difference between this energy to this energy is going to be the difference in the quantized energy states, and that's going to emit a photon in of radiation that comes out at that particular wavelength corresponding to that energy difference. All Bohr model. Cool? So much of this is right. So much of this is wrong. But I think it's really important for you to recognize, one, how do you think about systems? And so knowing that you're looking for two things, the location of the electrons and its energy. And in the location of the electron, you have to make certain assumptions about how you define where that electron is located. And this goes back to that picture that I drew. And we're saying, okay, here's the electron, here's the nucleus, here's the Coulombic potential between the two. We're going to introduce what are called boundary conditions. And we're going to build on these boundary conditions about where the electron can be found. What's the boundary at which you're going to find an electron or be likely to find an electron? If this is my nucleus, odds are I'm not going to draw my electron way over here. Okay. The other thing is that I want you to think about how we approached determining the energy by looking at the kinetic plus the potential, two types of energy. And what we're going to do is we're going to build quantum states by thinking of both the kinetic energy that's bound by the potential energy. Cool? Okay. Again, you won't be doing any homework problems on this for a while. This will come up later, but I think it's really important to know what we're building from. So this is the Bohr model. I will let you decide what parts we keep and what parts we get rid of. Go team. Bye.